In this video, we'll take a look at a few examples of how to use the payout annuity formula. A payout annuity is something like an annuity, except you're starting with an amount of money. It's still a compound interest account, and you make regular withdrawals from the account instead of making deposits. And so you start with this chunk of money, you withdraw at regular amounts of time, and eventually the account goes down to $0. So again, you're making regular withdrawals from an account, so the amount decreases over time, and it still accrues compound interest in the account just like it normally would. It's just a diminishing amount over time. Here's our formula. It looks a lot like the formula for annuities. Sometimes this is called the present value formula, and that's what this PV stands for. This is the present value, or you can think of it as the amount of money that you have at the beginning. So we'll think of this maybe as the initial amount, or PV for present value. The other variables are the same letters used, and they correspond to the same things as in the annuity formula. So D is what was the deposit, but now it's a withdrawal. So that's a withdrawal. K is the number of compounding periods per year. R is the nominal rate, so that's like the interest rate on the account. And N is the number of years. So again, just like in annuities, year is the basic time interval. So we'll take a look at a couple of examples of how to use this account. And the actual algebra is going to look a lot like the algebra in the annuity formula. Okay, so our first example, we'll be solving for the payment or the withdrawal. Payment and withdrawal are the same thing. They're both lowercase d. So in this case, you've just graduated. You have all these student loans that you have to pay off. So let's say all these student loans get consolidated into one account. And after your grace period ends, you have to start paying back. So let's say in total you have $60,000 of student loans, and you want to take 10 years to pay them off. The loans accrue interest, and it's compound interest, just like if you were saving money, except now it counts against you. And so you have a nominal rate, 6.25%, and it's compounded monthly. So our question is, if you want to pay off the student loan over 10 years, $60,000, how much is your monthly payment? And this is basically a solve for lowercase d type problem. So we use our formula. Present value is d, that's what we want to solve for. I'm just recopying this so we have it here. And we'll plug in what we know. So the present value, that's 60,000. That's the initial amount that starts in the account. That's what we have to pay off. D is what we want to solve for. And the rest of this we know. So this is 1 plus R is 0.0625. That's our 6.25%. It's compounded monthly, so K is 12. And we're going to pay it off over 10 years. Notice the negative here. And it compounds 12 times per year. So now we have to solve for D. I'm going to take, first of all, this 0.0625 over 12 to the other side. And so on the right side, we're left with D times all this stuff. So I can simplify this in a moment. So all this stuff in brackets, this is all one number basically multiplied to d. Therefore I can take this bracketed factor and divide it through to the other side. So I get d is this, 60,000, 0.0625 over 12, that stays, divided by this entire bracketed expression. And 10 times 12 is 120, so I can just replace the 10 times 12 with 120. Notice the exponent, negative 120, it's not on this 1 over here. It's only on this parenthetical piece. So here are some decimal approximations of these. So we have 60,000, 0.0625 over 12 is approximated by this 0.0052833. And then plugging in this exponential piece, I have 1 minus roughly 0.536133031. So then plugging these in, I get about 312.4998 in the numerator and 0.463869 in the denominator. Combining all this together, I get D is approximately 673.68. So this would be our monthly payment. Pay off $60,000 in 10 years, 6.25% compounded monthly. Your monthly payment is $673.68. And that solves our initial problem. We may also want to ask, because there's a lot of talk about student loans costing a lot of money. Of course, the monthly payment is pretty expensive, but you might be interested in how much do you have to pay in interest? In other words, how much does this loan cost? And when we say how much does a loan cost, that means how much do you have to pay beyond the principal that you borrow? And we borrowed $60,000, so we need to know how much interest is there. So we need to find out how much did we pay in total, and then compare that to how much we borrowed, which is $60,000, and the difference between the two will be the cost of the loan. So the total paid is our monthly payment, $673.68, times the number of payments that I have to make. And if I pay for 10 years, 12 months per year, that's 120 payments. So this comes out to be $80,841.60. $80,841.60. So the difference between this amount that we pay and the amount that we borrowed, which is $60,000, that must be the interest, and this difference is $20,841.60. So this is the amount of interest that we pay. That's quite a lot of interest. It's a lot of interest because it's a lot of time. 10 years lets the compound interest have a pretty heavy effect. Okay, so that's solving for payment. How about another example where we solve for time? So in this situation, we have a balance on a credit card. So we have $1,100 on this credit card that gets 24.49% interest, which is kind of high, but fairly typical credit card rate. And it's compounded daily, which is also typical of credit cards. And let's say we pay the minimum payment, which for this card happens to be $35. Then how long will it take us to pay off the card? In other words, how long will it take to get zero balance? And so for this, we use our present value formula because this is a payout annuity. We start with a chunk of money, it accrues compound interest, we make regular payments, and the balance eventually gets to zero. So our formula after plugging in looks like this. 1100 is the present value, and here we need our payment, but notice our payments are given as monthly payments, but the interest is compounded daily. So we need, before we plug anything into this, we need to compute from our monthly payments, what is our daily payment? And here we have to make a bit of an assumption because each month has a different number of days. So we just make the assumption that months have 30 days. 30-day months. This is not an assumption that holds true all the time, but on average we'll say 30 days, and this will introduce a little bit of rounding error, but for the most part it'll take care of it. So if we pay $35 per month and a month has 30 days, then I'll take the $35 and divide it into each of the 30 days, and I get roughly $1.167 per day. So I put 1.167 here. Again, that's our daily payment. We pay $1 and roughly 17 cents per day. So the rest of this we know, except for the time. Our interest rate is 24.49, so it's 0.2449. Compounded daily, so we go with 365. Another assumption that a year has 365 days, which is not always true. And then we have negative 365 times n. Remember, that's number of years times number of compounding periods per year. And so we need to solve for n, which is buried within this exponent. So we try to get it isolated. So I'm going to take this 0.2449 over 365 to the other side, multiply both sides, divide the 1.167, and now I can take this 1 to the other side. So let me get an approximation of this first. Yeah, so if I take this 1 over, it's going to be minus 1. And then over here I have negative what's left. So now I want to get rid of this exponent. I want to factor it out, so I take natural log of both sides. So natural log of all this. When I have natural log of this side, that becomes negative 365n times natural log of what was in here. So I can't forget this negative. Ran out of space. Okay, so now we can plug in all of this, and after you divide everything out besides the n, here you'll get negative 365 in the bottom, times natural log of negative 1 plus 0.2449 over 365. And that's n. So I won't put you through any more of this agony, and I'll just tell you roughly what n is. It's about 4.09, and that's in years, because remember that's the standard time unit. So again, going back to our original question, you have $1,100 on a credit card. It accrues 24.49% interest, compounded daily. If you make a minimum payment of $35 every month, how long will it take to pay off the card? Just over 4 years. So I think this 0.09 is about a month, which means it's about 49 months. So let's ask just an additional question. Okay, let's say the same situation, and you do take those 49 months to pay off the card. How much interest do you pay? So you took just over 4 years to pay it off. You paid the minimum monthly payment. How much interest do you pay? Or in other words, how much did this loan cost you? Well, you did pay $35 a month. And you paid that for 12 months a year for 4 years. And if you multiply that out, you end up with no, let's do this a different way. So let's say you just paid for 49 months. Maybe this is more straightforward. You paid $35 a month for 49 months. So you have $35 times 49 months. How much do you pay in total? That's $1,715. And there will be a slight error at the end because you probably overpay that last month a little bit. But if your loan was for $1,100 and you paid $1,715, then the difference must be the interest. And that's $615. So that's our interest. That's how much essentially you paid the credit card company to finance your $1,100 and let you pay it off for 49 months. So this is how much the loan costs, and it's how much interest that you paid. So back to the payout annuity formula, just like in the annuity formula, we could try to solve for R, but it shows up twice in here. It's going to be pretty difficult to solve for. So that's going to be given to you. K is usually given to you because you have to know the details of the account before you can start to figure out how much you have to pay, how much you need to borrow, etc. So that's all we got for payout annuity.